I will start. Hello, everyone. I'm Ivan Kulesh. I'm a PhD student in QTech, Delft University of Technology. And today I'm going to talk about one peculiar effect we found out accidentally in our samples while we were looking for Andreev physics. So let me start with the motivation for this study. And the motivation, of course, is in many studies in this talks, in this kind of forum, is of course combining superconductivity and quantum Hall effect. And why do we want to do it? Well, there are actually like a lot of cool features, interesting behavior predicted in these systems, in the combination of these systems. So for example, it was predicted that one can achieve artificial topological superconducting state when bridging together quantum Hall H states with a narrow superconductor. Or for example, it was predicted that it's possible to carry supercurrent with the quantum Hall H states. So quite rich physics in the combination of this phenomenon. But the simplest system one can look at is just single interface. So just a superconductor and a quantum Hall H state. So let me briefly go through this physics, though, of course, more will be said tomorrow, I guess, at the conference. So even this single interface with a superconductor and a system in a quantum Hall regime is not as boring. Incoming electrons in the H state quasi-classically experience this cyclotron motion, and when they encounter superconductor, they can Andreev reflect as a whole. And then they continue this Andreev reflection, so kind of alternate between electron or Hall quasi-particles. Quantum mechanically, of course, if one consider this, one would find out that this Andreev reflection results in the formation of so-called chiral Andreev H states. So there are actually, they come in pairs, this chiral Andreev H states. And what is more interesting, they can interfere with each other. So they predicted if they propagate coherently along the interface, along the superconductor, they can interfere, and the resulting quasi-particle can be either electron or Hall at the exit of interface. And for example, the probability of finding a Hall quasi-particles oscillates with the length of the interface, but also it depends on the difference of wave vectors of this pair of Andreev H states. So one can imagine, for example, controlling this difference of wave vectors with the system parameters such as gate voltage or applied bias. Moreover, it is very cool that in such a system, one can envision possible measurements to kind of like probe this behavior. One just needs to apply some bias, so bias the upstream H state with a current, which will result in some chemical potential. And then, of course, one needs to ground the superconductor, so the Cooper pairs resulting from Andreev reflection can drain into the ground. And then just measure the chemical potential downstream from the superconductor. The excessive population of holes, for example, will change the chemical potential, which will result in negative voltage. So this interference signal is predicted to be observable in simple transport measurements. And actually, the signatures of these facts were observed in graphene. So in a group of Gleb-Finkelstein, they observed the oscillating downstream resistance as a function of gate voltage and also as a function of current. So actually, what would you expect from this chiral Andreev state interference? However, there are complications in this system because in reality, of course, the interface might be disordered. And as was shown in the paper by Antonio, this disorder can also mimic these oscillations, actually. So more studies are required. And also we can benefit from using different platforms. So of course, this physics is not limited to graphene devices. We can benefit, from example, from two-dimensional electron gas. Let me elaborate. So first, two-dimensional electron gas, it's not a semi-metal, so we can use depletion control with the gate. We can kind of define some structures with gating, with depleted regions. Also, 2DEC offers scalable fab, so it's just a top-down approach in nanofabrication. Moreover, there is another subtle feature. So in two-dimensional electron gas, one can have intrinsic spin-orbit interaction. And this might be important when considering coupling spin-polarized H states to a S-wave superconductor. Then spin-orbit is actually required to kind of flip the spin and couple spin-polarized H to a superconductor. The particular 2DEC we are working with is indium antimonide arsenide ternary 2DEC, and it has some desirable properties. So, for example, the effective mass is very small, and lambda G factor is large. This kind of ensures the large energy separation between Landau levels, both in terms of cyclotron energy and in terms of Zeeman energy. Also, it has strong spin-orbit interaction, which in principle is beneficial for going to these spin-polarized regimes. And also the presence of arsenic makes the bending the interface with a metal or superconductor favorable, so you don't form a Schottky barrier here. Yes, Anton, do you have a question?
Yes. Is this a typo that the aluminum antimonide layer and the one aluminum indium antimonide are micron thick?
Yeah, so there are two monolayers of
got it. Yes, I see.
Yeah, it's two monolayers. Yeah, it's actually kind of some technicality to prevent aluminum chemically intermixing with the indium antimony and forming a compound. This structure actually allows for very good coupling. This epitaxial interface with aluminum, it's very nice. But the problem is, of course, that aluminum is not type 2 superconductor, so it cannot survive high out-of-plane field required to enter a quantum Hall regime. So first step of our fab is actually to remove this aluminum, and we have a 2DEC on the surface. So we proceed with just depositing type 2 superconductor. We use usual e-beam lithography, then we do some surface treatment. So usually this is just some very gentle plasma etch, and in the same chamber we deposit superconductor. And for a superconductor, we use either molybdenum rhenium or niobium tinitrate, both type 2 superconductors with a very high out-of-plane fields, higher than what we need to enter quantum Hall regime. Now let me, with this kind of scheme of fab outline, let me go to the real device. So we start with defining the actual region of 2DEC, highlighted in pink here. So this is our Hall bar. And then we deposit our superconducting contacts, in this case, niobium tinitrate here. So we have like a bunch of contacts. And of course, we also need some normal contacts for comparison and for regular measurements without any superconductivity. I'll return to this also later. Now, I already said that 2DEC are not semi-metal like graphene, so we can benefit from some extra gating, and that's actually what we designed. So here we place extra gates close to, well, basically covering this superconducting interface. So we just deposit the dielectric and then on top put some golden gates. So if we zoom in here, we basically have the split gates controlling the length of the interface. And this might be actually a very cool feature for this superconducting interference business. So the probability of finding Hall, right, it kind of oscillates with the length because it's interference process. And of course, one can control this difference in momenta of Andreev H state, but also it's kind of cool that we can think about controlling length of this interface by just putting more negative voltage to this gates and then kind of squeezing the interface. So that's why we have this extra gates there. And of course, we need to put a gate on top of all the device, global gate, to control the density, the chemical potential and the density of the device. So we gate from the top. It's also done through putting like extra layer of dielectric and then depositing metal. So with this device, we have very simple measurement protocol. we apply field, so we like put it in a dilution refrigerator, we apply out of plane field and fix certain gate voltage. Then we apply DC current for the device. So we drain it at a superconductor. We measure longitudinal and transversal resistance, so usual Rxx and Rxy, so we can determine that we're in a quantum Hall regime. And we also measure downstream voltage from the superconducting contact to look for these signatures of Andreev physics. So here is the typical Venn diagram and also a line cut on this on the right. So we basically sweep the gate voltage and field, and we see that we observe well-defined quantum Hall plateaus, which shows us like fixed values of Rxy and 0 Rxx, 0 longitudinal resistance. And we can stay at fixed field, for example, 7 Tesla here. And here is the line cut. We see that we can achieve nu equal 1, nu equal 2, nu equal 3 filling factors. So let's stay, for example, at nu equal 1 here and measure downstream resistance, so the quantity of interest. We can measure it as a function of applied current, and what we're looking for these oscillations of downstream resistance, kind of signatures of interference. And indeed is what we observed. So here is the voltage, and here we take numerical derivative, which would later we'll just refer as resistance. So we see that downstream resistance actually oscillates as a function of current, which is already a good sign. So this is kind of encouraging. Then what we can do next is we can vary the temperature. So it is predicted that with temperature, if the process is coherent, of course, temperature kind of decreases the coherence length until it becomes smaller than the interface, and then you don't expect any clear interference pattern, so no oscillations. Well, indeed, it's what we observed. So here we increase the temperature from about 300 millikelvin to about 1.5 Kelvin, and we see that oscillations actually dying out. So this is agreeing with this picture of coherent Andreev H-state interference along the interface. This is actually what we expect. Now, the next parameter one can vary is the gate voltage. So it is also predicted that the gate voltage changes the difference of momenta between Andreev H states, and thus it should change the interference pattern. And on this plot, we show the map of, so we stay at fixed gate and field, and then we vary it in the small range. So here about 15 millivolts. And we vary the current, and we see that there is actually some pattern, but it's not entirely clear. So we need to zoom in. And once we zoom in to increase the resolution to 1 millivolt in gate voltage, we see that there is actually very beautiful lines of different slope. And we note also that they kind of alternate between negative and positive. So we see negative values of downstream resistance, and we see positive values of downstream resistance. And this is again kind of all fits into this picture of Andreev H-state interference. Now, what another thing, of course, to check to really like prove the origin, well, to kind of add to this picture is dependence on bias at larger and larger values. If we revisit this picture, we actually like need to consider that there is upstream H-state going from the basically injector of current and then encountering superconducting electrode. And the voltage of this upstream H-state proportional to the current. So it's basically just your Rxy times current. And since Rxy is quite large, so in quantum Hall regime, it's like tens of kilo ohms, small current should already drive it above the gap voltage. So gap voltages are usually for the superconducting gap, a few millivolts, well, order of millivolt basically. And then once you're above the gap, you don't expect any Andreev reflection. So the quasi-particles, electrons, they just enter the superconductor and they don't Andreev reflect. So you don't expect any signal once you bias above the gap? Well, unfortunately, it's not what we see. So we increase current further and further until we actually here go to 3 microamp. This is very large current, so it's like order of magnitude above the gap if we convert it to the voltage of the upstream edge. And this already indicates that these oscillations, they don't have Andreev origin, because this already contradicts our expectations. Now, to kind of further kind of prove this statement, right? So to further elaborate, is it indeed Andreev or non-Andreev origin? We can measure with respect to the normal contact. So here we have exactly the same shape and location. Contact is a superconducting one, but it's just titanium gold. So it's kind of control electrode. And I can say that it's very important for all these kind of measurements to have control electrodes, preferably with the exactly the same fabrication, exactly the same details, just the difference should be that it's not a superconductor. So we measure with respect to this normal contact, also downstream resistance. And what we see surprisingly is we see similar oscillations. So they also go negative. So the downstream resistance from the normal contact also turns negative, negative and positive. The signal alternate as a function of gate and as a function of bias. This is quite surprising, but one may wonder, maybe this actually relates to the fact that this is downstream. So this is actually not like typical measurements you do in this quantum Hall devices, downstream resistance. Maybe it's like something specific related to the fact that current actually drains at this electrode, that this electrode is grounded. So we decided to revisit our longitudinal resistance measurements. So here again is a typical gate dependence at a fixed field, 5.5 Tesla of longitudinal resistance. These measurements are just usual lock-in zero bias scan. So we just, we don't apply any bias and we just sweep the gate voltage. And we can go through quantum Hall plateaus. And we see that there is nothing suspicious here at the first sight. Everything looks very flat and nothing is interesting. But let's actually look a bit closer. So let's focus on specific plateau, for example, filling factor of 4. And then now we know approximately the range of gate and bias when these oscillations appear. So we can basically do the same scan. We see that surprisingly, these oscillations also appear in RxX once we apply certain bias. So it is very easy to overlook them. We also actually see that they kind of suppressed at zero bias. So when you measure with lock-in, it's very easy to just overlook this behavior. But when we do this bias sweep, and also we have very high gate resolution, we see that there is very clear pattern. So these regions of negative resistance and positive resistance, they have certain slope in this map of gate versus current. What is also interesting that these oscillations, they're probably of the same origin we actually measured from downstream from normal and superconducting contact. So they also disappear with temperature. As soon as we ramp up the temperature, those oscillations amplitude die out. So for example, we can plot the normalized peak amplitude versus temperature, and we see that, indeed, it goes to zero. Above 500 millikelvin, we already cannot resolve them. And the more pronounced at low temperature values. So of course, the question now, how can we actually see these oscillations? What is the reason for negative longitudinal resistance? Is there like anything that can explain this behavior? Well, one potential explanation is coupled edges. So it was actually proposed by Butiker that if we have impurity in the system, so you can kind of see the zoom in here, if we have impurity state and it is coupled to multiple edges of the device, then it is possible to achieve not only positive, but also negative values of longitudinal resistance. In this, for example, 4-terminal measurement, we measure longitudinal resistance between these two terminals, and it is possible to achieve negative signal, but only when specific conditions are met. So there are like certain restrictions on these coupling values, and this is already one model which can, in principle, explain this behavior. Now, to kind of compare this to what we see in experiment, it is also interesting to look in the parameter space where exactly we see these oscillations. So here again, the typical RxX plot measured with lock-in at 0 bias versus gate. So we go through several values of filling factor. And we can kind of have this low resolution map of these oscillations, so bias versus gate voltage. And we see that, I mean, of course, here we don't really clearly see this slope because we now know that the slope requires very fine gate resolution, but we can still see that these oscillations are present, but only if we go towards the lower filling factor. So at the beginning of the plateau, if we go, for example, from 5 to 4, we see that actually there is certain region completely devoid of oscillations, then they become abandoned once we move higher up. So how this kind of corresponds to this impurity picture? Well, in the literature and like experimental studies associated this region of going towards lower filling factor with the disordered regime in a whole bar. So your bulk actually in this state comprises of puddles of compressible regions, and you have kind of incompressible bulk, but with the puddles of compressible states. And probably, well, it's our understanding that maybe these kind of puddles somehow couple the edge states, and they're responsible for these oscillations. Now, since the transport, we expect the transport to be happening in the bulk, the next logical question one may ask is, what happens if we increase actually the size of the bulk? So if we make the whole bar larger, will this suppress the oscillations? And this is actually what we can observe. So we made this device, which consists of the large whole bar, and then it goes smoothly to a smaller part of the whole bar. And what we expect is maybe like in the larger size, larger part of the whole bar, it's the coupling of the edge states is less efficient because just the distance is larger, and the oscillations would be suppressed. And actually, it's indeed what is happening. So the oscillations are kind of suppressed. There is a very large region which is completely devoid of oscillations. Though at the same time, if we measure simultaneously in the small part of the whole bar, the oscillations appear already at like some current, and they are more abundant, basically. So the size definitely matters in this case. Now, there are also a few other things we can kind of consider with these oscillations of longitudinal resistance, which might reveal some light on their nature. So, for example, the gate dependence, one may wonder if this gate dependence is actually universal for throughout the sample, or is it something local? So if it like changes throughout the context. And we found that it's not universal. So if we measure RxX on different contacts at same filling factor, so all other parameters are the same, we measure these two values simultaneously, we observe that the slope of oscillation is actually different. This might be related to the fact that maybe we measure on the opposite sides of the whole bar, and actually like the side which we bias, which kind of upstream from the grounded terminal, is not, let's say, equivalent to the side which is grounded, because I mean here the potential, at least classically, you expect it to be 0 on the edge state once it equilibrates with a grounded terminal. But of course, it also has some dependence on gate and bias. So the picture might be more complicated due to bulk transport, and maybe there is some specific distribution of voltage which affects this picture. Now, another thing is these oscillations also move the field. So the regions of negative and positive resistance, they have some certain field response. For example, it might be that this impurity level moves in energy with the field. So maybe it's like confinement changing with the field. This might be one possible explanation. But also this behavior is kind of very smooth. So there is no jumps, or like it doesn't care about vortices entering your system, for example, superconductor, which something one might expect in the case of Andreev physics phenomena. Another interesting thing is these oscillations also respond to the local gate. So we have these gates which originally were envisioned to control the length of the superconducting interface, but we can kind of see if there is any response from these gates on these longitudinal resistance values. We just keep this contact floating. So just some local, basically probe some local depletion of the 2-deck. And apparently we actually see that longitudinal resistance on both sides changes when changing this split gate. So this localized probe somehow affects this coupling between edge states or these impurity levels. What might be happening is maybe it somehow changes the area of the hole bar, and thus it changes the current density, and this eventually changes some potential distribution inside the bulk, affecting our transport. So that kind of summarizes my presentation. In conclusion, we observed the oscillations in longitudinal resistance in quantum Hall plateaus, in specific regions in quantum Hall plateaus, and we also observed that these oscillations, they have specific structure. So there is they depend on gate voltage, they depend on current, and they also depend on field. Also, one thing to, of course, keep in mind that the values are both negative and positive of this longitudinal resistance. And the negative values doesn't necessarily mean that any Andreev process is happening. So we observe these oscillations relative to the normal contact and also in longitudinal resistance. So Andreev physics is kind of not the culprit here. And it is very important to distinguish these oscillations from real Andreev physics. So one need to be very careful about the size of their samples and about the regime you operate in. So these oscillations can very easily kind of mimic Andreev physics, and yeah, one need to be very careful. So thank you very much for listening. I'm ready to answer your questions if you have any.
Yeah, I actually have a question. Yes.
Yeah, hello.
Thanks for this interesting talk. Have you measured the transparency of the superconducting electrode in this sample?
Yeah, so actually these measurements I presented, they're from a bunch of different samples, and we had quite different quality of contacts. I cannot say exactly like the value, like the best value of transparency we had, but well, we had quite significant supercurrent. Like we also made Josephson junctions with the same fab flow to kind of make sure that we have nice superconducting contacts. And we measured like large microamp, large supercurrent for relatively small junctions. So we know that the contacts are quite good, but also some contacts were not as good. So with like very small supercurrent, but regardless of the context, we've seen this behavior. So it doesn't really correlate to the quality of the contacts. That's what we found out.
How about the enhancements, let's say, at small fields, maybe at zero field?
Yeah, so we
getting the reading from?
Yeah, so we for good superconducting contacts we observed some enhancement, but we also observed the dip at zero bias, indicating that still there is some barrier. So of course those contacts, they're not as good as epitaxial aluminum. They also have some barrier. Yeah.
So it seems to be naively that this Bütikow picture would also be consistent with, let's say, incomplete equilibration at the superconducting electrode. So if the coupling is not as good, maybe one would expect similar behavior. So it would be nice to actually measure, let's say, convince yourself that you're measuring a good transparency in the superconducting contact, and then further hunt for Andreev behavior.
Well, I don't see how like imperfect contact can explain, like limited transparency can explain negative values of resistance, and also how it can explain the dependence on gate voltage and magnetic field. So this pattern is kind of very clear, and yeah, I mean, I don't know if like just considering imperfect contact can explain that.
Thanks.
Yeah, Antonio, you also have a question?
Yeah, thank you. Thank you for your talk, Ivan. So did you check the bias dependence for the larger samples? So I'm wondering, for example, if you see like a suppression of this oscillation at higher bias.
Yeah, so for larger sample, this is actually bias versus gate dependence, and they appear at large bias, but if you move further in the quantum Hall plateau, there is very large region where you don't see it. So up until we measured, like until this bias, we don't see, maybe like eventually they will appear. I haven't checked like larger biases, but there is considerable region where it's clearly zero, while for the smaller side, yeah, we have these oscillations.
Yeah, okay. I was picturing actually the opposite. Like if at some larger bias, you actually see like a suppression of these oscillations.
Yeah. But surprisingly, yeah, it's actually the other way around. So they still persist. Yeah.
Also, another question. So these two plots are for like the full quantum Hall plateau, or like you still see like a constant.
It's just going,
yeah.
It's just going for one plateau. So yeah, this is basically, I mean, here for larger side, you don't see the transition towards the end. So it's still at the plateau here, while at the small side, yeah, you're already going into the transition. Yeah. So it's like one nuclear 4 plateau.
Okay, I see. All right, thank you.
Yeah, maybe Link Fei. I see you have a question.
Give me a sec.
Hey.
Or nice talk. So sorry, give me a sec. Where's my? Can you hear me?
Yeah.
Okay, good. So there's a few questions I want to ask. Like first, I would say like those stripes are interesting. Like, did you try to measure a gate map, like a finger gate versus the back gate, to see the slope difference?
Finger gate, you mean this one? For like this one, for example?
Yeah, that finger gate. So just to say like where the location is, right? If it's closer to the interface, that finger gate would have a stronger capacitive coupling to whatever that the disorder is. But your back gate would be less efficient correspondingly. So like you just want to compare the slope to see if you can pin out the position of the disorder.
I see. Yeah. Well, we haven't compared different split gates. Yeah, I guess maybe you can, and maybe this can actually like.
Also the global gate. Try to vary the global gate a little bit.
Yeah, so the global gate, we know that there is certain slope for these oscillations with the global gate. We can just compare the slope, but we can see there is a huge difference, 3 orders of magnitude, because for the split gate, we vary it actually from like 0 to -2 volts, which is all the region we can do it. And for the global gate, we see kind of similar change in the oscillation when we vary order of like 1 millivolt. So it's like 1,000 time difference.
So that's kind of indication the disorder actually inside the bulk, not close to the interface.
I guess one can say that, yeah, maybe it's indeed indication that there is like very small level arm, very small coupling of the local gate, but it can also be other effects, like maybe you change the density of current because you can change a little bit the shape of the whole bar, and then it also affects this behavior.
So one thing I want to also make is like, during our measurement, we also see some spurious signal. Like typically it's in the biased gate map, you would see an anti-symmetric signal. So that's an indication of a bad contact. Basically, usually if you think about IV curve instead of dVdi curve, that means you're gonna get a bump or like a dip in the IV. So basically at zero bias, your contact is slightly floating away. It's a little bit similar to here, but it's not exactly similar. But in terms of Andreev physics, you would expect it to be symmetric, because if you compute the dispersion of the Andreev estates, you will see it's becoming smaller. The dark key is becoming smaller in both directions. So typically it is symmetric over bias. I mean, sure, at the high bias it would be anti-symmetric, but exactly at the zero bias, it should be symmetric.
Yeah, I guess. And also you expect it to be maximum like the amplitude of the signal for Andreev physics at zero bias, right? Because if you move like away, your basically amplitude of Andreev reflection goes down, and then you above the gap, and that's it, you don't see anything.
Yeah, but it's not like unusual to see this kind of fluctuation in a bad contact. Like we typically, you will see it. Like it's just like you have to distinguish between whether it is Andreev like physics, or one of the things like you did really good is to compare the signal strength to RxX, because I mean if it's from the bulk disorder, you would expect the same strength of oscillation. So that's what you saw.
Yeah, indeed.
And also the vortex jumps is also important. You also did that. So
yeah, so this kind of regular checks. All right, maybe we should move on to the next question. Anton, I've seen you have your hand raised for a while.
Yeah, thanks. So just to understand, if you use the one of the normal, if you do the same experiment with one of the normal contacts playing the role of the superconducting one, you also see similar oscillations, right?
Yes, exactly. So if we measure, with respect to the normal contact downstream, we see exactly similar oscillations. Yes.
And is their magnitude also are most of their properties comparable as well, or? Yeah,
exactly. So magnitude is also comparable. Yeah. So it's order of like tens of ohms, basically.
Okay. So, but if you take a thicker contact, say one of the sides, are you able to do a similar measurement as well? So not the one with the fine gates, but
I see. Yeah, unfortunately not, because all these contacts we cannot kind of simultaneously ground them and measure relative to them. So this we don't know how it changes if we make the contact longer, for example. Yeah, this. We can't really say for sure.
And another quick check. So do you know if it makes a difference whether you which of the two split terminals you bias and which you ground? So on which of the two split terminals you ground and on which you measure the voltage? I mean, so here you measure VD across this loop and grounded the other one, but you could as well do it the other way around. Do you know whether this makes a difference or not? This is just to rule out some of the contact physics.
Yeah, so we kind of checked all different combinations of contacts, and we always observe similar patterns. So yeah, I don't know.
Similar is fine, but does the signal change? So if I replace the sign, if it changes the sign, it will look similar, but specifically I'm wondering if I compare exactly the same plot but with the terminals wired the other way around, how much will they coincide?
Anton, I think I can answer your question. Like basically you would expect to be different because say like you measure one contact nearest contact downstream at 1 voltage, and the second contact another voltage. But that voltage will be equal to the first voltage plus the in-between XX. And because you measured a non-zero XX, so you should just measure both together.
No, sorry, but my question is different. I'm asking about the how you wire the same metallic electrode, not related to the quantum Hall, just the properties of the. So in this schematic right now, look at the rightmost electrode. There's the ground is attached to its upper side and the voltage probe to the lower side. And I'm asking what would happen if I interchange these.
These like but these two, they just have like zero resistance between each other, so it's like metallic superconductor.
Yeah, it should be superconducting or metallic, I agree, but do you know that for sure, or is this the expectation?
No, this is the expectation of this. We checked that it's like zero, but we actually, I guess you need some kind of extra terminals to measure it. So you would want, I guess, to properly check this path. You would want to have 2 terminals on both sides, I guess, to like.
No, I mainly imagine just hooking them differently. So
yeah, and then seeing, well, I mean,
I don't mean just flip the source and drain.
Well, the ground and the voltage probe.
These two. Yeah, no, I mean, we haven't specifically checked for that. No, this we haven't checked because we didn't really expect to be any different. Well, also, I mean, we observed this behavior for both like leads made out of different materials, like, for example, very thick gold or superconductor, and we always measure the same. So
I know we check that a lot, and it's on Euro to see a difference. It's typically most of the time it's the same.
Okay.
Also, since we observe these oscillations in RXX, where there is no ground at all, we just measure between 2 contacts in RXX, similar oscillations, then it kind of rules out that there is anything peculiar about this kind of region.
And another question I would like to ask is about so if I look at this plot and several other, there seems to be an anomaly close to small bias. The signal seems to be weaker at
indeed. This seems to be a typical pattern for all the measurements. So it's kind of contradicts what one would expect from Andreev physics indeed, but it's what we observed. Usually this is suppressed, and then it kind of makes it easy to overlook when you just measure RXX with lock-in. You don't apply any bias, so you usually like apply small AC bias, like some 10 or 5 nanoamp around 0, and then you kind of just overlook this behavior.
All right, thanks a lot.
Maybe Osborne, sorry if I'm pronouncing your name correctly.
All good. Thanks for talking, Ivan. I was curious, have a couple like material related questions. Do you have measured the mobility peak as a function of gate for these materials? I'm just curious.
We know mobility versus gate dependence. So our peak mobility is about, since it's surface to deck, so it's not as large, it's about 25K. 25, okay. Cool. The mobility, and the density, I cannot remember the density exactly, the number now, so, but
that's fine. And also regarding, you said that you kind of tested your superconducting contacts for the critical current. Have you done any checks at high field? So similar fields that you use for when you study interior quantum Hall?
No, we don't. We didn't for this specific contacts. No, we only measured their properties at 0 field, like for example, Josephson effect, but not at high field. No. So this is kind of also unknown and might be very relevant for these studies. That's true.
All right. Cool. Thanks.
Yeah. Thank you. Maybe James.
Hi, can you hear me?
Yep.
So what I was wondering is, based on the fact that your slope of your lines as a function of current and gate voltage look really consistent and nice. So to me, it seems like there must be consistent current path giving rise to these oscillations. So I was wondering if you considered the possibility of there being counter-propagating edge states at the edge of your Hall bar, maybe due to an accumulation layer at the edge of the mesa.
Yeah, so I guess you can explain negative signal with the counter-propagating edge states, indeed, but I don't know if one can also expect similar behavior from counter-propagating edge states, like similar dependence on slope and field. And we haven't specifically checked for them, like if it's indeed related to like counter-propagating edge states or not. Yeah, so I don't know, I guess like the border of our 2-deck, I would expect it to be in a pretty similar condition because our gate kind of covers everything, and then, well, you kind of similar distance from, I mean, like it's a surface 2-deck, right? So like the conditions, well, I mean, at the boundary, you just like that, right? You like just have very similar, I would imagine, conditions as like on the top. So you have like gate covering everything also. Well, here it's not shown, but for example, the boundary, you would also have dielectric of similar thickness and similar gating. So yeah, I don't really think I would expect necessarily some like different edge physics at the interface.
Sorry, when you have a counter-propagating edge state, you're not going to say negative. The only thing you're going to say is positive, because it's equal to a nanowire, you know, it's two-way transport.
Well, I guess this is like the differential resistance, yeah, right? So I guess what I was picturing is building a little interferometer based on the downstream and upstream modes going back and forth.
Yes.
And then when you're applying a finite bias, I think you could get negative differential based on the phase changing.
Yeah, I mean, some behavior maybe can kind of like fits into this pattern. Yeah, I guess.
But yeah, maybe not.
Yeah, I see your point. Yes. Well, if you the absolute value of the voltage, that voltage cannot fall out the window with bias and drain. Instead of differential.
Sorry?
Like if you measure the absolute value of your voltage instead of differential, and that voltage has to be between the 0 and your bias window in this kind of case. But if you measure Andreev, it will fall out. You see my point?
No, I don't think I'm actually following.
Like your lowest potential you applied is the drain, and another one is source. Yeah. Any informator, like in this kind of region, you would expect to generate an absolute value in between this 0, this bias window, right? So if you measure that absolute value of the voltage, it will always in between. But for Andreev physics, you fall out.
But for Andreev physics, I don't see how it can be larger. I mean, you also...
It's negative.
Yeah, it's negative, but absolutely it would be also like limited, right? You cannot have like more holes than you have electrons. You cannot have like Andreev reflection more than a unit probability.
Yeah, but like I'm saying, like you're injecting a voltage positive, you're measuring absolute value of a negative voltage.
Yeah, I mean, but also, I mean, if we look at the voltage, for example, here, right?
Yeah.
You go to positive current, the voltage goes down. I mean, there is some value, but it's just offset, right? So, I mean, we cannot really, you can consider like these values, they're not really like meaningful by themselves, like because there is always some measurement offset in voltage measurement equipment. So you can say, okay, at 0, I'm at 0, and then I increase the current, the voltage decreases, basically. So you have immediately negative resistance. You don't have to like go further up, basically.
Well, this I disagree. This absolute value have meaningful because you know in our case you measure it to be negative at 0 bias. The absolute value, not the differential.
Well, I mean, here for this particular case, it's positive, yes.
Positive, yes.
But
so I mean, indeed, like
it doesn't mean
interferometer will generate this kind of effect because it's falling in between the biasing window. and oscillating.
But I mean, we not really apply any bias. So then at zero bias, you anyway would expect 0 voltage because your bias window is 0. So you shouldn't look at these values particularly.
Oh,
that's what I'm saying.
Interesting.
All right, maybe we should move on to the next question. Lucila, right?
Yeah, hi. Thank you for the talk. I don't understand why the oscillations seem to die out at nu = 3 in your parameter space
let's
slide,
see. Yeah,
the location in parameter space.
Mm-hmm.
Yeah, you have like large oscillations
at
the nu = 2 and the nu = 4 plateau, but at nu = 3, like they die out. I mean, what's the physical explanation for that?
Yeah, I guess here we just don't really have like very well-defined nu = 3 plateau. So if we like not all the plateaus, they have the same size in the parameter regime. So here we probably just have already a breakdown of quantum Hall. We just apply like relatively small current, and we already not in a quantum Hall regime. So just not a well-defined plateau, I guess.
Okay, but your longitudinal resistance seems to be quite close to 0. I mean,
but it's not the only factor. Yeah, so it's close to 0, but only for very small range. So if you compare the range, like how long in terms of gate span is close to 0, like it's, I don't know, a few times smaller. I mean, we also observe these oscillations at nu = 3, but also they would be limited in bias. So if we increase bias further and further, we're already like in a breakdown of quantum Hall, and then we just see like positive slope. Yeah, I don't have a plot here, but eventually, yes. So if we really zoom in here, we would also see oscillations also at nu = 3. So it's not really related to like specific feeding factor. Yeah.
Okay.
Thank you. Any more questions? James, Linkfei, do you guys have more questions? Or
sorry.
I just.
Sorry, not for now.
All right. Thanks a lot. Thank you everybody for the questions. I think it was interesting discussion.